Why? Yeah. Oh no, like that's just what we did for like science.
All of these. Oh my god. All in one.
No, the transfer me. Like right after that.
Okay, guys, happy Friday. Today we will talk about simple loops, and I will demo my quadratic equation formula solver thingamabob for you. I will pause after that and let Kendall do her thing. What's your question, Kendall?
What is the world's fastest computer?
Okay. It's a very ambiguous question with hopefully a nice ambiguous answer. And then if we get a chance, I guess we'll go on and get into chapter 3. So let's carry on here. Actually, I think the first thing I'll do is demo my version of the quadratic equation formula. I don't know how many of you guys have submitted, but if you see something today or I emphasize something today that you haven't done in your program, don't just say it's dead to me. Get it out, get it in there, and resubmit it. And make sure that you use the same file name that you used the first time, and it'll just overwrite the old one. All right. So here's my quadratic equation solver. It starts off by explaining what it is and how it works. So you print out some information to the user, and then it asks for coefficients. Remember that one of the things I specified in the assignment is that all three coefficients be given on the same line. So here is a prompt, and this thing in the square brackets is a hint as to how the program wants the data. It wants three numbers separated by spaces. Let's see. A nice quadratic formula would be something like this. So as you're writing your program, you want to make sure that it actually works. And so what you should do is test it on values that you already know the answer to. So for example, if I enter 1, 0, and -1, what kind of equation is that? What's that equation? X squared minus 4. And if you solve that thing, you move the 4 over to the right-hand side, you take the square root. What are the answers? Plus or minus 2. So if this thing is functioning correctly, I should get some report that says there are two real solutions and they are plus or minus 2. So I hit enter. For the coefficients a equals 1, b equals 0, c equals -4, there are two real solutions, 2 and -2. This stuff here, user feedback, to let the user know that, yes, I got the coefficients from you and this is what I think they are. And then present the answer. All right, let me run it again. A really simple one with complex roots is this guy. So that's x squared plus 4 equals 0. You move the 4 over to the right-hand side, it becomes -4. Now you have x squared equals -4. If you're stuck in the real numbers, there's no solution, but I'm letting you go to complex numbers. In that case, the solution is plus or minus 2i, where I is the square root of -1. This is something that you probably picked up back in, I don't know, algebra or algebra 2 or something like that. So it may have been a long time since you've thought about these things. So let's do that and let's see what happens. There are two complex solutions, and notice how I give them to you. I've actually tweaked the assignment, I tweaked it I think Monday or Tuesday, to give you a little bit of flexibility on how you present these complex numbers. You can present complex numbers to readers in two ways. You can say x plus iy where x is the real part and y is the imaginary part, or you can just present them as ordered pairs, where the first slot is a real number and the second slot is the imaginary part. So this is exactly equivalent to plus or minus 2i. This is much simpler in a way than printing out x plus iy or x minus iy, and I'll talk a little bit about that in a minute. So is everybody okay with, or does everybody understand this notation as, you know, here's the real part, here's the imaginary part, and I do ordered pairs? Rebecca?
Why are there negative signs?
Yeah, that's a weird thing about C++. There are actually two zeros in C++. There's a positive 0 and a negative 0. And you can't imagine why you would ever possibly want to use that. But the numbers that I entered and the formulas that I use internally to my program end up creating a negative 0, but it's 0. Dylan, question?
Mm-hmm.
Okay. Danielle?
How do you get like that tab? Like it goes in? Right?
This guy here?
Yeah.
And these guys up here? \t. \t. Make sure you're reading your book. All right. Let's go on and look at this thing, and let's try 0, 1, 1. So here I'm asking the program to solve x plus 1 equals 0. What did I tell you to do in this particular case? Print a message and ask for the data again. And keep asking until the user gives you a non-zero A. So let's look at that. So I type 0, 1, 1, and it prints out the message, A cannot be 0, and then it gives me a prompt for these coefficients. Let's pretend I'm really belligerent. 0, 1, 1. A cannot be 0. Oh, okay, whatever. 1, 1, 1. And then I get the answer because A is not 0. That's what I want to talk about next, is how you get this repetitive prompt that keeps going until it gets something that it's happy with. And this leads me to the notion of a simple loop. So let's go back to the example directory. Let me make a note here to you guys. I added a link to the class webpage down here, in class examples, and it's not very sophisticated, but if you click on in class examples, you'll see a list of the programs, the little programs that I write in class. So if you ever want to go back and grab some of those, or just see what I did, there they are. Okay. And to that end, whenever I'm programming, I'll do it in this examples directory. Let's look at 2013-01-25 simple loop .cpp. All right. What I'm going to do is really similar to what's going on in the program, but I don't want to show you. I don't want to write your program for you. So I'm going to do something that's similar. I'm going to repeatedly ask for an even number, which we kind of talked about last time, and I'm not going to stop asking until I get one. All right. So let's get an integer and let's ask for an even number. And let's read it in. So at this point in the program, in the variable n is whatever number the user entered. While n %2 is not equal to 0, and I'll explain the syntax in a minute. Do the following. Cout, let's say error, please enter an even number. And then we'll repeat this whole thing right here. And then down here we'll go cout. You entered n, which is an even number. All right, let's see if this does what we want, and then I'll explain. So enter an even number, 4. You entered 4, which is an even number. Good. Let's see what happens when we enter an odd number. And let's try it again. And again. And then say, okay, whatever. All right, let's look at how this is happening. What we're using to get this repetitive behavior is something called a while loop. It's one of 2 main kinds of loops that you have in C++. How does it work? Well, the program, remember, executes from top to bottom, statement by statement by statement. So declares a variable, prompts for a number, reads the number, and then it gets here. And a while loop will execute everything between the open and curly brace and the closed curly brace. It will execute that over and over and over again as long as its condition is true. So let's see how this works. I come in, enter an even number. Let's say I enter 4. So now it goes on to the while loop. N is 4. 4% 2 is what? It's 0. Is 0 not equal to 0? It's hard to think about. Is 0 not equal to 0? It's false. No, 0 is equal to 0. So this thing here evaluates to false, which means the while loop doesn't happen. It doesn't even happen once. And it skips to the end brace and carries on. So if I type in a 4, which is what we want, an even number, this while loop never happens because the start condition is false. And we skip to here and it says you entered 4, which is an even number. That's the easy case. Let's think about the more interesting case. Let's pretend I entered 5. Now I get here. What's 5% 2? 1. Is 1 not equal to 0? Yes, true. Which means this thing is odd. We're going to print out an error message. We're going to ask for the number again. We're going to read the number again. And guess what happens? You don't keep going now. You go back up to here and you check n again. So let's say I enter 7 here. Go back up here. 7% 2 is 1. 1 is definitely not equal to 0. So the loop happens again. Please enter an even number. Ask for a number. Get the number. Go back up here and check. Let's pretend now I enter 4. I go back up here. 4% 2 is 0. 0 is definitely equal to 0, which means the loop stops. Yes?
What will happen if you entered like a negative?
It should be fine. We can test it. Yeah. I confess to not really thinking too much about the modulus of negative numbers, but it appears to be doing what we want. I usually think about modulus in terms of positive whole numbers, but it looks like it's working. Good question. The quickest way to answer a question like that is to just try it. You can't break these things. Not with software anyway. Yeah.
So sometimes you use the \n and then sometimes you use the n-l.
Yeah, I'm pretty random that way. I'll tell you, like, usually I would have put a \n here, for example. I'll tell you when I usually use endline and when I usually use \n. If the last thing in the cout statement is a string, in quotes, I usually use \n. If the last thing in the cout statement is a variable, I usually use endline. But as you can see, I don't really stick to that rule very closely, but that's my tendency. Yeah, it's a good observation. And yes, \t will let you do indenting. So for example, maybe I want this all to be indented one. And now everything's indented. And you can use the indenting to kind of emphasize different features, so I'll leave that to you guys to play around with. Yeah?
So I noticed you enter your \n and your \t inside the.
Always inside the quotes.
But doesn't it also work?
Nope. Nope. These are \t and \n are secretly just characters. Like ERROR is a string of characters. This is secretly just another character. In fact, it shows up in the ASCII table. Somewhere in here, there's \n right there, and its ASCII value is 10. And there's probably a T in there. Yeah, there's a horizontal T, and its ASCII character is 9. So even though it's comprised of two characters, \n or \t, the compiler sees it as one character.
And I had another question that has to do with the sum program there.
Mm-hmm.
So you said that it'll save 0 as both a positive 0 and as a negative 0. Is that true for all things? Because
Only for floats or doubles, but not for ints or other kinds of ordinal types. Okay. Yeah, it's part of the IEEE standard for floating point numbers that there's a positive 0 and a negative 0. I have never seen a useful application of negative 0. Yes?
If you want two tabs instead of one, do you just do \t, or do you do \t?
\t. Each one of those guys is a character in and of itself. Yep. Okay, Kendall. Come share with us what the fastest computer is right at this moment in time. Yes, you can. So after Kendall's done, what I'm going to do is we're going to spend a little bit of time sketching the quadratic equation program so that you'll, if you haven't already done it, you'll have some roadmap to follow over the weekend. If you have already done it, what I'd like you to do is compare what you've already done to what we're going to sketch out today and see if, in fact, your version is as efficient or well organized and possibly make some modifications based on that. Are you ready, Kendall?
Yeah. All right, so I'm doing a presentation on the world's fastest computer. And you have to understand that when we're talking about the world's fastest computer, we're talking about a supercomputer. And supercomputers are computers that perform at a rate of speed that is far above other computers. So usually what they do is they have multiple processors, which help speed up anything that the computer can do. And the primary use of supercomputers today is in scientific computing, because oftentimes you have so many processors, like you're going to need lots of funds and lots of money to keep them from overheating. So generally the only sorts of institutions that can run supercomputers of such a magnitude to be even on like the list for top fastest running computers in the world have to be universities or national labs. And in fact, the world's fastest supercomputer right now belongs to Oak Ridge National Laboratory. And this is supposed to be a picture of Sequoia, which would give you a good example. Maybe I can find it on the internet.
I don't have QuickTime installed.
Darn. But yeah, I don't know how to spell that. Sure.
I'm sure Google will figure it out.
There we go. Okay, so basically this is what a supercomputer looks like, and these things are freaking huge. They take up whole rooms of buildings, and they often have whole rooms designated for cooling systems as well. And let's see, back on here. Okay, so the world's fastest computer is Titan right now, which actually went online early in 2013. And I'll show you a picture of that too, seeing as this is not gonna.
Is that a picture that was that a picture or was that supposed to be PowerPoint?
Oh yeah, that's supposed to be a picture.
What the heck?
I don't know. I can't spell. Okay, so this is Titan right here. And this thing is super fancy. Let me get onto the BBC. Titan. Is it doing it?
That's weird. I don't know what it's just right there. Yeah, good try.
Okay.
Really? Setting up.
Or maybe it's just waiting.
Need to upgrade your computer.
Seriously? Okay, there we go.
There we go.
It's just a mere threat of my presence. I was gonna smash it.
No.
Come
No.
on, stupid computer.
BBC.
Yeah.
Okay. Let me see if this is the one with the images.
I think what it is the wireless connection in this room, right at that podium, is pretty unreliable.
Okay.
I had
This
a lot
is
of
not
trouble with it
it.
last semester.
Maybe it'll be this one. Oh, shoot. Ah, here we go. Does this have more pictures?
Click on the little flash thing.
Wait,
Upper
what's
left-hand
this one?
corner. So I have flash blocked.
Okay.
Do you need sound or anything?
Well, there's like a reel of pictures
Okay.
that was going to be shown about the
Jaguar
computer.
is a computer that we first
Like, the
installed
stacks
at
of
Oak Ridge
processors
National
as we're setting it up.
Laboratory in 2005.
And
It was
whatnot.
a Cray XT3 supercomputer that could do 26
When you have
trillion
PowerPoint.
calculations per second.
Such an issue.
Today we're
Okay,
doing
well,
an
I'm just gonna
upgrade
talk to
of
you about the computer,
Jaguar,
and then
and
we
we're
can
going to turn it into
do
a new
that.
machine that we
Okay.
call Titan. Titan will be
Okay,
over
so what makes
20
Titan so
petaflops,
impressive is that it
or
performs at 20 petaflops, so it
quadrillion
can make
calculations
over
per second.
quadrillion
So another 10
calculations
times more
per
powerful.
second.
What
However,
makes Titan
this
special
obviously
and
is very
interesting,
expensive to
this
run
time
because
is
it requires
that it
over
uses a new type
7
of
megawatts of
architecture
energy
that has
each
graphical
year. So obviously you can
processing
see
units
why
that,
like an
gamers
ordinary person
use
wouldn't
to,
necessarily
make
be able to
their
possess such a
video
supercomputer.
games run very, very
It also has
quickly.
710
So
terabytes
graphics
of
is
RAM,
really
which
a
are about as much
computational
as a stack of
problem. So same
iPads
sorts
7
of
kilometers
computations,
high.
calculations that are behind
And
computing
from
the scene in
Jaguar,
a video
the
game
computer that they upgraded
can be
it
used
from,
to
Jaguar
compute
had 79,000
the components
processors,
of a
and they
scientific
added on
calculation, to
40,000
compute
more
interactions
processors.
of drug
This
molecules,
thing,
to compute
the
airflow over a
electricity
wing,
costs
to
$7 million
compute
to
the
run, but the
climate.
computer
You
itself
can
costs
think of it
$60
really
million
as kind of like a time machine.
to run.
We're able to do in a much shorter
Yeah,
amount of
and
time what
so a lot of what these
perhaps
computers are used for,
a
especially sensor run
non-supercomputer, a regular
by
server
facilities
in
like
the data
national
center
labs, is they're
might be
used
able
for
to
a lot
do,
of scientific
but it would take
calculations.
1,000 times
Titan
as
received
long. It might not
79
even be able to
proposals,
do it all.
even though it's
For
been
medicine,
online for less
example,
than a
the work we're doing on
month.
drug design.
And
So you
these
have
are
a
some of the
small
first
molecule
projects that are
that's a
going to be
drug
sending
will-
data to
will
Titan
be like
to
a key
compute.
in a lock.
So it's going to be used for
And
testing
what we
new
do with
drugs,
computers
simulating
is we
the
try and see
supernovae
how
core
the key
collapses.
fits in the lock and if it will
For
fit.
global climate
A
stuff, it's
guy
going to
in a
model
research
human
lab
skin
in
and
a
blood flow
company
at the
will try
molecular
maybe
level.
several hundred of
And they're
these
also going to use it to
potential
optimize
keys to see if
biofuels
they
and
fit in the
engine
lock.
combustion
Now
turbulence.
with a supercomputer in one day we can do tens of millions of these things.
Titan is
So we
actually
can
so
screen
loud that
them
when you're in the room and you're
computationally,
inputting your data into the computer, you
millions
have to
and
wear
millions of
earplugs and
potential
then
drugs to see if they hit the target.
headphone
So we
type
can simulate
things over
larger
that as well.
systems. That means we can
And
see
Titan
things
is actually
how
meant to
they
be
work
used for
together,
private use.
rather than just
So
having to look
if
at
you're a
them
researcher,
by
you can submit a
themselves.
proposal,
That's
and if they
critical,
don't
of course,
accept
to
it,
understanding
then you
things.
can't use your computer
Titan
for the data.
physically is also one of the largest computers in the
Supercomputers
world,
like this
not just in
are
computational
so useful
power, but
to
in
anything
size.
because they're
If you look at
constantly
the
helping us
size of it, it's
advance
200
computer
cabinets.
technology.
Each of those cabinets is about the size
Scientists
of a
like to say that
refrigerator.
some supercomputers
So
of
this is about
today
the
will
same
be everyone's
size
computer
as a
tomorrow.
basketball court, for example.
And another thing
it
to
uses
understand
as
is
much electricity
there's
as
always
a
like a
small
new
town.
world's fastest
So we
computer.
have 24
These
inch
computers
in
only hold the
diameter
titles for probably a
pipes
year
that
or
we
less
run
because people are
42
always
degrees
trying to make
Fahrenheit
bigger,
cold
better, and
water
faster
through,
computers to do
to
more
just
things.
cool this computer.
So, and
But
it's
that's
highly
not
likely
really the
that
most
Japan will
important
finish
thing. We don't
its
buy these big
next
computers
processor
just
and add it
because
onto
we
their
wanna have the
computers and
biggest toy in
make
the
Titan
world.
obsolete
we
by
need
July.
more powerful computers because we have really important problems.
Titan is
that
at
we're
Oak Ridge
trying to
National
solve.
Laboratory,
We
which is
want
in
to
Tennessee.
cure all known
And
diseases,
the United
solve
States
the world's energy
Department of Energy
problems,
has
and
the
understand
honorary
the
title of
function of the
having
living cell. So that's really a question of
in
really
the
high
top 20,
throughput
they have
brute force
5
number
machines
crunching.
Over the next
all of
few
which
years,
are at
we're
national laboratories. So
working
like
towards
Sequoia
what we
at
call
Lawrence Livermore, they have
exascale, which is
Chinook
10 to
at
the
Pacific
18th
Northwest National
calculation,
Laboratory.
10 with 18
Los
zeros
Alamos
after.
had
Now, what we'll be
two,
able
but
to
they're
do with the
taking it
exascale
offline because one
is
of
we'll
them
have
like
enough
caught on
power
fire.
to simulate
Because
every
these
single
things
atom in a
overheat with,
whole
you know,
living
thousands and
cell.
thousands of
That means we'll be able
processors.
to
You're
try
gonna
and
get a little bit of
predict
steam.
if something will work as a drug
But,
and what all the
anyone have any
side effects will
questions
be.
about
This is
supercomputers?
amazing
Pretty freaking
potential.
tight.
And everything we do is simulating things to try and understand them.
Yeah.
And the supercomputer will help
Yeah.
us to do that.
So you were saying that, you know, future supercomputers like this will become personal computers
Yeah.
in the future?
Actually, technically, like a lot of you can actually buy supercomputers today because the only thing that qualifies as supercomputer is having multiple processors and performing at like an above average processing level.
So it costs, what, like $7 million to run?
Just the energy alone to power the computer. But like cooling costs, usage costs can cost up to $60 million.
But will that be able to go down enough so that it can be
Yeah, definitely not for a computer of this magnitude. The room that Titan is housed in is actually 100 meters long, and they utilize all the 100 meters for its processors. If I had like the pictures, you could see like the stack of graphic cards that they have. They're just like hundreds of thousands of graphic cards for the computer alone.
All right, thanks, Kendall. Okay, back to my simple computer here. Let's talk about, that's data structures, ignore that. Okay, let's talk about sketching this thing, this quadratic equation solver thing, a little more in detail. All right. So what I'd like to do is this is something, you know, you don't normally do what I'm about to do for a small program like this. This is something that a professional developer or even a scientist would do for a much larger, more sophisticated program. But it's certainly worth outlining this program to get an idea of how someone would plan a program. The quadratic equation solver, as I mentioned, is fairly straightforward. What I'd like to do is kind of sketch the major components of this solver. So what's the first thing that you have to do with this solver if you're planning this program? I want to think not quite in terms of syntax, but in terms of actions, tasks that need to happen.
You need to figure out what the input would be and what kind of output you want.
So I need to prompt for, for coefficients. I think there's one thing that has to happen before prompting for coefficients.
Right after.
Right, okay.
Test to see if they're okay.
So test, in particular, A not equal to 0. Right, so you want to make sure that you deal with that. Danielle?
Before that, maybe explain what.
Yeah, I like that. Instructions. Okay, keep going. So you've prompted for coefficients, you've tested for A not equal to 0. Now what?
Look at the variables to see what you're going to need to do to them, which is like 3 options.
Right. So what's the key piece of information that you need? You know, like how do we look at the variables to figure out which of the 3 cases we have?
Categorize the discriminant.
We need to compute the discriminant, right? So we need to compute, go away. Compute D equals B squared minus 4AC. I would literally have a D in my program. So once I'm happy with my coefficients, I would literally just compute b squared minus 4ac. Once I figure out d, then Eli, yeah, so now I can drop into an if statement. Why do you keep doing that? Okay. Okay, so we check D to see which of the three cases. All right, next.
Can we just run a quadratic formula?
Sure. So you could then compute the solutions. And I'll put a parentheses S out there because in some cases there's only one solution, and in one case there's one solution, in two cases there's two solutions. Okay, I've computed the solutions. Now what? I have to report back to the user.
And maybe
yeah. So Rachel's comment was, I want to provide user feedback in a sense. You could tuck that in here. We could call that a separate step, user feedback. Or you could consider user feedback as part of the reporting process, whatever that happens to be. Now, this is kind of how you start, and then what you do is it's kind of like writing an outline for a research paper, right? You get the big sections, and then you're done with that, and now you go in and you look at what has to happen in each of the little sections. What are the parts of each section? So, for example, and I'm not going to expand it here, but let's, step 0. There's not much to expand there. I mean, I guess you could write out, if you wanted to, what the instructions were actually going to be. But frankly, that's something that I think you can handle at the time that you're actually writing the program. In fact, most of this planning for a simple program like this is something that you could handle at the time of writing. The second one, prompt for coefficients and step 1 and step 2, prompt for coefficients and test for a not equal to 0. We've talked about how this is going to happen, right? This is going to use a loop. Just like the one that I used when I was asking for even numbers. So we'll use a while loop there, and we'll just keep going until we're happy. Which means when we get to step 3, a sort of a precondition for step 3 is we're now happy with the coefficients. That's kind of a precondition before you actually go on and start computing things. Now, 3 might not really deserve its own line because 3 pretty much is precisely what we say there. The reason I put 3 in there is it's important when you're writing a program to identify important pieces of information. And D is an important piece of information. It triggers the behavior of the remainder of the program. So we compute D as b squared minus 4ac, and now we drop into step 4. Step 4 I'm going to sort of write out here. So expanding on step 4. How are we going to do step 4?
You got if statements or like nested ones, maybe?
They don't have to be nested.
Or just like if else statements? They
don't even have to be if else. They can just be this. If D is greater than 0, then do some stuff. If D equals 0, then do some stuff. And if D is less than 0, then do some stuff. And that will do exactly what you want, the 3 different cases, right? Because if D is positive, it'll do all the stuff in here. And if B is positive, what will happen to this if statement? It gets skipped, right? And what will happen here? Skipped. Okay. Yes,
So
Janet?
if and else don't actually come in pairs in a program. You can just have ifs and no else.
Exactly, yes. Exactly. And that doesn't mean that you couldn't formulate, you couldn't do this in terms of ifs and elses. There are lots of different ways to accomplish the same logical framework that this does. But I think this is the clearest. So yes, I would compute D, and then I would just have these 3 separate if statements to do the work of computing the solutions. So in fact, in each one of these, you're going to compute the solutions. Okay, so that leads us to step 5. Step 5, you already have D. Once you have D, computing the solution, remember what the general quadratic formula says. The quadratic formula says that x is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. In terms of the discriminant d, this is actually negative b plus or minus the square root of d over 2a. Right? Now, you've already computed d, so there's no reason to do b squared minus 4ac again. Just use the d that you already have in the correct context. Now, C++ is going to throw up if you try to take the square root of a negative number. So in the first case, for d greater than 0, we can literally just use this formula. This is fine as is. In the second case, when d is equal to 0, the formula is actually a lot simpler. What's the formula when d is equal to 0? Negative b over 2a, exactly. And that's something that the program can figure out. Notice how I wrote that, negative b slash 2 slash a. Be careful when you're doing this. For example, if you do negative b slash 2 star a, that's not going to do what you think. What's going to happen if I do that? It'll divide by 2, and it'll multiply by a, and that's not what you want. What you want to do is divide by 2 and divide by a. So there are a couple of ways to solve this. One way to solve it, if I insist on using multiplication, is to do what? Parentheses. And that solves that problem. Or the first thing that I wrote up there, b and 2 and a. Remember, again, we're going way back into like middle school and high school math here. Order of operations, right? And all of those order of operations laws that you learned in high school and middle school actually hold in this particular case. This operator, the minus sign in front of the b, is called the negation operator. It's not the same as subtraction. It's called negation. It takes whatever b is and negates it, turns it into its negative. This slash 2 says, okay, now take this number and divide by 2. And then this slash a says, take this number and divide by a. Multiplication and division have the same precedence. And when they are listed in an expression, they go from left to right in order. Addition and subtraction have lower precedence than multiplication and division, and so you have to keep all of that in account. If you have used a TI-85, which many of you have, the precedence rules are exactly the same as like a TI-85 or something. When in doubt, use parentheses. Something else to worry about here. Do I have to worry about getting integer division versus regular division in this expression? Do I have to worry about it? It depends. like, for example, do I have to put a 2.0 in there or something to make this thing behave correctly? It depends on how A and B are declared. Exactly right. Now, in this program, A, B, and C should all be declared as doubles. And in that case, this is going to behave correctly. And by correctly, it's going to do regular division as opposed to integer division. All right, let's look at the last case, which is a little tricky. For d less than 0, if I try to use this formula as is, in other words, if I try to do something like negative b, let's just do one of these guys, and then we'll use the square root function. So there's an expression that if d were positive would be fine for computing one of the roots. Right? This is an expression that you could use right up here for d greater than 0. But if d is less than 0, this is not what you want at all. What's going to happen if d is less than 0? The square root's not happy. The square root doesn't like taking the square, doesn't like dealing with negative numbers. So, how do you deal with this situation? Well, remember that when d is less than 0, what kinds of solutions do you have? Complex solutions, right? So, what I'm going to do is we're going to sort of fork a little bit and talk about how to represent complex numbers in the output. So, in a math book, a complex number is written a plus ib, where I is the symbol for the square root of negative 1. And you may or may not remember this, but back when you first learned about these complex numbers, you could represent the complex plane, the set of complex numbers, as ordered pairs, A and B. Does that somewhat ring a bell? So that would be the point A plus IB, the complex number A plus IB. Another way to think of these guys is as ordered pairs, A comma B. And there's a whole algebra about how to multiply and add and divide these things, which I'm not going to go into. For our purposes, all we care about is the real part and the imaginary part. A is called the real part, and B is called the imaginary part. So let's look at what happens when d is less than 0. The quadratic formula says that the solutions are given by negative b plus or minus the square root of d over 2a. I'm going to break this up into negative b over 2a plus or minus the square root of d over 2a. That's basic algebra. I just take the 2a and I divide it into b, and I take the 2a and I divide it into the square root of d. We still don't quite see the real and imaginary parts yet. I'll pull that out for you right now. So, d is the same as negative 1 times minus d. Agreed? D is the same as negative 1 times minus d. So it's a bit of algebraic trickery here. Now, the square root of -1 is I. So let's keep going. Oops. And so now we have something that looks a lot like a plus ib. And the a and the b up there are different from the a and the b down here. This is the real part. And this is the imaginary part. Now, what's beautiful about this way of writing things, when d is less than 0, if d is less than 0, what can you say about minus d? It's greater than 0, and hence the square root function is perfectly happy. So when you get into this third case, d less than 0, the real part of the solution, let's call it r. I don't want to use r. What do I want to use? Let's use rp. What's the formula for the real part? Negative b over 2a. And what's the formula for the imaginary part? Oh, and let me write it in C++ terms. So what you would do in this third case is you would actually get yourself a couple of more variables. Variables are cheap. RP and IP. And you would compute RP as negative b slash 2 slash a and IP as square root yada yada yada. And you can rest assured that when you're in this third case, you know that d is negative and hence negative d is positive. You can rest assured that that expression for IP will be well defined and will work. And then what's your output? Just that. And, sorry, the other one as well. And negative IP. Remember, they come in complex conjugate pairs. So your answer for the third case, the easiest way to do it is to compute the real part and the imaginary part separately and then print them out as ordered pairs. Where do things get crazy with this other notation? So what's hard about printing a plus ib? I can show you a few things that are kind of annoying about this. In the case where a and b are both positive, then this will be perfectly fine. This will look exactly like what we want. Let's consider, for example, the complex number 2 and say negative 3. In this notation, it would be 2 minus I 3. What's hard about that from a programming perspective? Yeah, getting the I between the minus sign. This is how it should be written. This is how you would see it in a math book. So how would you get that output? You would have to look at the real part. If it's negative, you would have to sort of insert this minus sign in the I and then print out the negative of the real part to get this thing to look nice, to get it to look proper. Let me show you another example that's annoying. Oops, 2, 1. Okay, that guy is 2 plus I. That's how you write the complex number 2, 1. It's 2 plus I. What's annoying about this one? If it's a 1, I don't want to see it. Right? In a math book, you don't see 2 plus I1, you just see 2 plus I. So you've got to suppress that. This is a good above and beyond if somebody's interested in it. If you can get this thing working and printing out nice complex numbers, I'll count that as an above and beyond. If you don't want to struggle with that particular issue, Just print them out like this and let the chips fall where they may. Dylan.
So A, B, and C are all double. Is that the same with D, Q, F?
Yep. Everything in sight here is double.
Is that because?
That's just because of what complex numbers can be and what the roots of quadratics can be. Other questions? Okay, just really briefly, in the time that I have left, I noticed over the weekend, as I was grading some things, it's really annoying. How many of you guys have had a chance to look at the upload program in a regular browser? If you go look at the upload web page in a regular browser, it looks like this, which is definitely nicer looking than the Lynx version. And one nice thing about it is it has this choose file thing, which then lets me go browse and find a file that I might want to upload. And because it has this choose file browser thing, there are never typos in the file name. This is something that I hadn't thought about, but there were a couple of you that when you tried to submit your program or your above and beyond program, you actually put a typo in the file name, and Lynx briefly flashes up an error message saying, you know, I couldn't find a file, and then it continues on and says, hey, you successfully uploaded this. I searched and searched and searched over the weekend to try to figure out where I could grab that, check that error, and I could not find anywhere on the web that would let me trap that error. So what I'm telling you right now is be really careful about using the exact spelling of your file name, or watch very closely if Lynx, for example, let me show you what happens if Lynx doesn't find the file. So there's a file called good.txt. I have no idea why it's there. And maybe I want to upload it using Lynx. And let's say I do good.txt, right? What's wrong with that? It's capital G instead of lowercase g. I don't notice. I just carry on my merry way. It's associated with homework 2, and I click submit. Watch really closely now. Can't open file for uploading. Thanks for uploading good.txt. Okay, if you don't notice that thing down there, you're going to think that you got away with it, but you didn't. And let me show you what happens on my end. Let's see. So there it is, good.txt, and if I look inside of it, and I have no idea why this is happening either, the file name is in there, which is not in any way what you want. And so just be aware of that as you move forward. Yeah, go ahead.
So if we want to use the online version, how do we find our file?
Okay, so one more quick thing before you go. I know I'm 3 minutes over. There's a program for Mac and Windows. It's called FileZilla. Free, safe, no viruses, open source software. You run this thing, you go to the math.whitman.edu, type in your username, your password. Hold on now. Oops, and I just did that. Put in 22 right here. That's really important. It won't work unless you put a 22 in there. In a second, what will pop up is, here's all my stuff in the math lab, and here's all the stuff on this computer, and you can just drag files back and forth. I think this is something that you might want to get used to doing. I'll try to talk more about it on Monday. Drag the file over to your computer, then launch the browser and upload it that way. Okay. Have a good weekend, you guys. Danielle?
If we did accidentally send out like an email or
If you did accidentally do that, yes, I'll let you know.
So that file thing, does that work for programs like I web and I wrote something on the
Anything, yes. Absolutely. Yep.
So how